Okay, that kind of looks like it's maybe working. Do we need this? Like, could I just like talk to you guys? All right, sweet. Um, cool. So hi, I'm Yonatan. Thank you, Andy. I'm gonna talk, the title is Everything Fails, Everything's Ambiguous. I am classically like a language person, as in like I back a decade ago when I was doing my thesis, was doing it on syntax. And then I moved from that towards robotics. And that means that the way I tend to view things is a little bit from that perspective. So sort of what is it that language background teaches you? It means that you always think about things in terms of pragmatics, in terms of theory of mind, in terms of, as we said, cognitive science, these kinds of things, because that's kind of the fundamental nature of what language is, why it exists as a concept. And so then as I've been moving increasingly into sort of the robotic space, there's these questions of like where those things manifest and what that looks like. And so I'm going to sort of start off by giving you like some of the like a one slide history that many of you probably know of like kind of where language and robotics have interacted. So there's much older work. So there's the classic stuff like Stephanie Telix is like the sort of OG of the space, Joyce Chai, like they're the people who sort of really laid foundations. But where we started to get a lot of excitement was from things like Peter Anderson's vision language navigation work, because it gave us a simulator. It was photorealistic, or sorry, real photos, so not even rendered images from people's houses. We had language instructions that we were attaching to them. And I was also interested in this space. And I was sort of what concessions people were making. So as an example, this is some stuff that we then did, I guess about a year or two later, which was called Alfred, where we used the Thor simulator. So it was all rendered, simulated objects and assets, but it allowed for interaction in a way that this did not. And we had underspecified language. So we had things like place to spray bottles. And the idea was that when you think about language, it's never the case that anybody actually says what they mean. I don't know to what extent, how many people know of Grice's maxims? Okay, we got like a couple. Okay, so there's this notion in language, which is that if I was going to spell everything out for you, it would sound really robotic. It would be incredibly weird for me to do that, for me to tell you everything. So the reason that we care about theory of mind in language, the reason it's so fundamental to language, is because everything in dialogue assumes common ground. It assumes that there's this process by which the two people identify what are the shared reference, and then I only give you the necessary information for the cooperative principle. So the idea here was that like, I really shouldn't give you all of these instructions. And that's something I'll come back to again. Now, these are in simulation. Things as we just saw, are much more impressive now. This is some work that we did like a year ago on sort of actually getting stuff running on a robot, and it tends to be much simpler. So it tends to be like, well, I have sort of a subject verb kind of situation. Then I'm sort of looking for a specific object. I'm doing pick and place tasks. So this is to say we have made progress. It is the case that we are seeing language on robots, whether at the scale that we just saw or sort of commodity robots that are a little easier for us to interact with. But it doesn't address this question of language being a social phenomenon. So I'm going to be mostly talking in the first part of the talk about some work by my student Tiffany, who's up there. And the basic idea behind this is to start asking a really, really simple question, which is what role does the physical human play in your interpretation of language? So if I change very, very little about language, or about the instructions that I'm giving a robot, but the person is present in the environment, how does that differ from what we were seeing on the previous slide, where we had a language instruction, we had instruction following for a robot? And so here's kind of the premise. We can start to think through what are the types of ambiguity that are present when we are interpreting language. So this is a caricature, obviously, but I get some sort of an instruction, like put a cup on the dining table. There's this little cartoon cup in the kitchen, a little cartoon cup here. And I can think about what are the types of ambiguity that the agent has to model as they think about this task. So, whoop, why is it not doing the thing? Well, there it goes. Okay. First of all, are there multiple cups? The answer to that clearly in this case is yes. So this is sort of like if we think like what does the agent need to be thinking about? Really important, is my current map accurate, right? So is it the case that I have actually accurately built this setup? There's more to it, but we'll use those as our examples. So I'm going to make one small change. Instead of put a cup on the dining table, it becomes bring me a cup. It's very simple. It's not something that we would think of as being sort of uniquely distinct. It's still a pick and place task. It's still the receptacle is just now the individual. So therefore, we have some of the same sources of ambiguity that we had a second ago. So we have, are there multiple cups? Yes, that's still an issue. Is my map accurate? Yes, except now there's this entity in the map that is potentially not stationary, right? So the person is moving around. And so I need to sort of figure out how to keep track of where they are, particularly if my attention is focused on something else. So far, I'm not saying anything that's that bright. You guys are like, everyone, this is all super obvious. And the way that we would try to address this if we use the standard instruction following paradigm from those existing data sets is sort of linguistically, in the sense that we would build out some stupid paragraph that would give us way too much information. Bring the dirty white cup that is half full of brown water. It's currently on the left-hand side of the coffee table. So the sofa, like we could do that. It sounds incredibly unnatural, obviously, because it's not the kind of thing we would ever say to a person. Why would we never say it to a person? Because the cooperative principle that we established at the beginning, which is not how humans talk. Okay, so we don't want to do that, but we have a lot of data sets that do that. So we have sort of this problem, which is that we have a bunch of data sets which are working on this sort of heavily focused on sort of visual grounding to something in the space. We have a lot of work, obviously, in the community on figuring out what are the set of basic primitives that you need to execute on. But this doesn't really quite feel like the right paradigm for us here as this person exists in this space. So I'm going to kind of caricature the literature a little bit in the following way. So these are some of the data sets plus one that I was talking about a second ago. If we have this kind of over specification, this sort of like, let me just give you every visual landmark you need to pay attention to in order to complete this task. That's sort of the room-to-room vision language navigation. But on the other hand, I have this sort of Alfred setup where I have the underspecified manipulation task or like object navigation where I'm trying to find something in the environment. It's super underspecified. And that this sits maybe somewhere kind of in the middle, and we're calling this situated instruction following. It'll be at ECCV, whenever the heck that is, I don't remember. So what are the things that need to be said in this setting? What is implied by an action? I'll come back to that in a second. How do I need to think about making sure that I am modeling the notion that my map is constantly stale? And really the big focus is on this notion of ambiguity resolution. So that's where we're coming from with this. Now, something I really like to do is present my own work and then shit on it. So this is a first step. And I would really, really appreciate lots of thoughts about sort of like, how do we bridge a bunch of these sort of simplification gaps between this and reality? But nonetheless, I think it gives at least a little bit of an outline of some of the thinking we've done about this space. So here's what this looks like. Habitat 3.0 gives us the ability to simulate at least simple human actions in an environment. So now I can go to that really simple example that I gave a second ago, bring me a cup, and now there's a me, which is nice. So bring me a cup, but crucially, I'll be taking a bath. So what's our ambiguity? What are the types of ambiguity that we need to resolve here? So first of all, where's the cup? Which bathroom? So pausing for a quick second, really obvious, but we need something in the model that is making explicit the fact that there's these two sources of ambiguity. They're both kind of related to mapping, but they're also potentially related to intention. And what I mean by that is that it's the nature of the ambiguity is going to change temporally as I sort of sit in the scene. So at the moment when this instruction was uttered, I may or may not be able to answer what to do. But the second that the person starts walking, well, if they're saying that they're going to be taking a bath, they're probably going towards the bath, right? And if so if they're walking towards this bedroom versus that bedroom, then I actually now have a resolution to that ambiguous question. Now, what you probably don't want for all of the social nap literature is particularly not a spot, because it's an insanely loud robot to have in your house. But you probably don't want a robot that is like literally sitting like at your heels, like trying to watch you go to the bathroom. So instead, you want something that's like a little bit more like understanding what is the minimal amount of information that I require in order to resolve this ambiguity. Therefore, what is the path plan that I should produce in order to resolve that sufficiently? Recognizing that there's other sources of ambiguity, for example, where the cup is, things like this. And that brings us sort of finally to this issue of this clicker keeps not working. The dynamic nature of the environment. So if I don't know where the cup is it because I'm not detecting it? Is this an issue with my own detector? Is it that the human moved it? And so that's sort of like, it's not something like a fundamental computer vision problem. It's just that I'm stale. And I therefore have this other source of ambiguity, which is when should I or where should I keep searching? So the idea is what I would ideally like to see. So I'm mostly describing a benchmark right now, but what I would ideally like to see is a situation where I'm able to like build some sort of a model that is keeping track of ambiguity around both the sort of temporal implications of the sentence, the spatial implications of the sentence, how sort of when my map was last updated, what I should do about it. So you could imagine, and we have some examples like this in the data set, things like if I'm looking for something that someone just interacted with and they were in one of the rooms, there's no reason for me to update my map about the rest of the house, right? The only damage that that person could have performed was in that one room. And so therefore, I should only consider that to be stale. So how do I kind of keep track of those types of things? And so this is a very simple setup where we think through 3 different cases. So the idea is that you probably have your robot in your house doing some sort of pre-exploration, building some initial map that it's going to be working off of. And so we'll call this phase 1 exploration. Let's see sort of where the human left everything. And then we have 3 tasks. So we have a pick and place type task. We have an object which has been moved, and we have some information about where it's been moved. And we have some sort of dynamic receptacle, aka the example we've been working through, where the human is moving. So, bring me the cup or put the cup on the end table, something specific like this for a known fixed receptacle. Bring me a cup, I moved it while washing my hands. Okay, so sort of that common sense reasoning about where they might have washed their hands, but then again, not all sinks because I see them and they haven't actually been in that part of the house. So therefore, I really shouldn't be exploring every part of this. And then finally, I will be washing my hand. In other words, I'm giving you some indication about where I'm going to be going. And so particular focus on these sort of latter 2, the dynamic object and the dynamic receptacle, are sort of interest here. So what does this kind of look like? Well, it's simulated. And so the following video, I think, gives everybody like a little bit of like motion sickness. But I have a house that I pre-mapped. I've got this human in the space, and sorry, but I follow to the point where I've resolved the ambiguity. I know which room they went into. Again, arguably, one of the, I think, sort of natural pieces of feedback is that if you deploy this, you would not want a robot that close to you. But I've resolved the ambiguity, and so this should be the end of that part of the exploration. That has been resolved. That referent is no longer unclear. I now need to move on to understanding the rest of the instruction. Now, this is just an initial attempt. This is an initial release. And so in this, we built out a bunch of baselines that are sort of try to copy whatever the state of the art is in instruction following and see how that applies over here. So I'm not going to go into this in that much detail because it's pretty straightforward. I have RGB and depth as input. I have some semantic mapping. I have some instruction. I have some sort of prompt that goes into pick your favorite planner. And then you try to have this, the language model in this case, basically try to reason through what does it know about the environment? How does that dictate what it should do? For example, should it be following the human at this point? Because it doesn't have enough evidence to understand things. Now, in any system, as we know, we're going to have a whole bunch of cascades of errors and issues. And so some things are going to be because perception problems. Some things are going to be because of reasoning problems. So we're going to try to disambiguate those a little bit. So oops, I don't know why we have a little slash there, but that's okay. We have test seen and test unseen. So these are going to be unseen are going to be houses that the agent has not been in at all versus new tasks in an environment they have seen before. So we can do pick and place. We can do the situated object. These numbers are not high, you may notice. The human here being the human as the receptacle. And then a sort of similar case on the right-hand side. So this is the full task where you've got perception errors, you've got reasoning errors, and everything else all falling apart. let's go ahead and make things a little bit Oracle for the moment. So I can fix all of perception and I get this nice little boost across the board, except it's still pretty clear that there's a dramatic drop off when we move from the situation where I'm just trying to put something in on a receptacle. It's just a mapping task. So this pick and place is, again, something we're all very familiar with. It's pretty close because we're just using simple language descriptions to our kind of standard tasks that we see in other things, whether it's, object nav aspects or Alfred aspects or stuff like this. And we're trying to kind of add this other aspect to it. Before you ask, there's only one person. Should there be more than one person? Of course. But in the first paper, there's not. So there's only one person. But that is like one of those places where things definitely should just improve, right? So that is sort of the main punchline for this first part. It's pretty simple. If you play with it and have comments, we would love them, about sort of thinking through some of these kinds of issues about how do you build at least an environment where we can start to study this question of where does uncertainty reside and how do you start to resolve it. The other thing that has come up multiple times throughout this is that everything fails. And what I mean by that is, for example, the green versus the blue here, right? Your perception is failing, but also the fact that none of these are 100% because your reasoning is failing. And the other thing we said on the previous slide and has become increasingly popular is that we're just going to use language models as if they're AGI that is going to do all of our reasoning for us, and they're going to do planning for us and stuff like that. And that's like a really, really tempting story. Like it's really, really nice to think that we can do that. So then this begs this question, are LMs actually robust planners, right? In particular, this work is on exploring recovery and awareness of failures by these students of mine. And this is on arXiv if you're curious. We are trying to, again, in a similar kind of way, just lay out some frameworks for how to think about these problems. So just trying to understand this. So let me give you a little bit of what that looks like. The first part is we need to formalize a little bit what we mean by tool use and what we therefore mean by sort of calling of APIs and things like this by language models. And so there's some input that you're providing. There is some context. There's the tool input itself. Then there's oftentimes this tool selection. So either that's because I'm doing code generation, there's a bunch of APIs I could reference, something like this. There's the tool output, and then this all goes back into my LM for me to start making my decisions. So if I start to think through this and say, wait, so what are the sources of error? Which pieces are likely to fail? And which pieces can be recovered from? And this is, I think, pretty natural to think about in any kind of, again, multimodal sort of embodied task. So for example, I have maybe some goal. I'm going to wash and slice the apple. I have some perception. The object detector will be wrong. Duh. That means it's going to detect some things. It may incorrectly detect certain things, or it may detect too many things because it sort of says that like has low confidence on a whole bunch of them. This gets fed back in. The LM is doing some reasoning about what it wants to do. There's the action planner and so forth. So we have this kind of recursive loop where we're choosing different tools. And there's these questions as to, are we providing the right input to each of those to choose the right tool? How are we interpreting the answer, stuff like this. So I'm going to start off for a quick second doing something that's not embodied, sorry, just so we can kind of control everything. So a faulty calculator was the simplest thing that we could come up with. So I'm not that great at arithmetic. There's a reason I have a phone. And even though that's the case, there are certain things that are sort of like heuristics that I have though, right? So if I have two numbers, I can't necessarily do that multiplication or that division or whatever it might be in my head. But if one of them ends in a 0 and I multiply them, I'm expecting the result to end in a 0, right? There's certain things that would give me a sense that if a calculator was broken, I would be able to at least detect that failure. And so what we did is we said, okay, here's a few changes that we could do, some perturbations we could make to a model, and we could see to what extent they're able to handle, like if the last digit changes, if any of the digits change, and so forth. Again, very easy for a human. So I'm going to spend a second on this plot. GPT 3.5, GPT-4, Command R, which is, if you're not familiar, Cohere's model, which was specifically for tool usage, Command R plus, Gemini 1.5. The black line is showing how well the model can answer a bunch of basic arithmetic questions. Just, nothing, no help. And all the lines, oh, sorry, let's start with the above it is if I give it a correct tool. So if I say like, here's a calculator that gives you the correct answer, then, to what extent does it trust it and does it use it and its performance go up? And unsurprisingly, it goes up. None of these are hard. We're talking like 4 digits or less, real simple arithmetic, the most basic stuff. So now what happens if I give you a calculator that has some of these failure conditions? What happens? Well, to different degrees, you can see tools, so slightly weaker models or models that were trained specifically to be good, oriented towards tool use have real overtrust issues. The tool said this was the answer, so therefore it's the answer, regardless of the fact that now I'm producing something that my original base model knew the answer to. So I'm ignoring what's in my parameters in order to use what the tool has given me, which seems a little bit problematic. And then some of these bigger models, or the biggest models we have right now, are basically just like ignoring the tool. And so we're not seeing those same sorts of degradations, but even there's some amount of difference. So they do not handle the last digit as well, for example, as they do like sign inversion. So if you make something that's supposed to be positive, negative, they're more likely to notice that error. But if you just change the last digit, they're more likely to just be like, oh, yep, well, the tool said that was the case, so we should move forward. So what we have here is a bunch of language models and an incredibly simple text-based task that they have been trained to death on, where they know the answer, but then failing once there's this the possibility of this other of the tool being present. Now, the way that we tend to handle this in the literature is through error messages. So the way that we tend to assume that this is not going to be a problem because we can come up with ways to address this. These are going to be our interventions. The standard thing would be, for example, with code generation, you say it doesn't compile. There's some sort of, the interpreter gives you an error and you propagate that back to the language model and you go from there. We're going to try a few simple things. Again, this is a calculator for the moment, so easy stuff. What happens if I simply, so oblivious is I don't do anything. What if I simply tell the model the tool might fail? Does that decrease its sort of overtrust? What if I give confidences? So for example, if I'm using an object detector, what if I actually take those detector scores and pass those in as part of what's going on so that it can reason a little bit about that tool itself? And then a checklist is asking it to sort of reason through error types. I do see that clock. I will be like, oh, and I see our next speaker online. So hi, I'm getting there. So we're going to use chain of thought and few shot and all those kinds of things, obviously, but I'm going to start off with the simpler case and leave the rest for the paper because the story doesn't shift that much. Command R plus, GPT-4, Gemini 1.5, all this is all questions that they know the answer to. So if I didn't use a tool, they would all get this right. So here's the Command R transition. So the no sort of disclaimer of any kind versus saying, hey, by the way, the tool might not be perfect. Here's GPT-4s, and here's Gemini 1.5. And so they're not, I don't have a trend here in general. I can't sort of give you a takeaway. What you can see, though, is that like none of these things are perfect. You can see that telling the model that there's a likely failure is useful. And so if you're going to use language models as planners, thinking about how you might want to try to incorporate that instead of trusting it. There does seem to be maybe some consistent benefit to like the checklist model, but not a consistent benefit to things like confidences. So we see Gemini actually degrade for when we give it sort of like, here's how well what the object detector scores are versus some of the other models. Okay. I'm gonna wrap this really quickly. So the thing that one of the key questions that we don't have an answer to, but that hopefully is now sort of bouncing in your mind is, when is a failure actually a failure? So in the calculator, that is a little bit easier. It's like I gave you 2 numbers, you got the wrong number, deal. Okay, but if I'm actually planning, so for example, if I have an action planner or something like this, here we have simulation in Alfred, and the tool is trying to figure out whether or not, or so your model is trying to figure out whether or not to trust the output of your planner, that is a little bit less clear, particularly with something like an object detector. So is it the case that actually it said tomato and it's an apple, it's good enough, it's close enough, we're still going to be able to execute correctly, right? So it's not the case that there's sort of these simple binary answers for any of these. So where does all this go to? Well, let's just shoot for the moon and say that what we really want is metacognition in our language models. So like what we really want is language models that have some ability to reason over what they know, some confidence about what they know, bringing us back to that original question of ambiguity, understanding ambiguity in the space, looking at what they're perceiving, and then being able to reconcile or reason through how to fix that. We have some initial things like the disclaimers to help. You can also do stuff like change your entire inference algorithm in order to try to make this more explicit. But I think what that's doing, or that's admitting, which is maybe a good thing, is that the language models themselves are not sufficient to do this, right? Language models do not have metacognition as a single straight through thing. You're going to use this as one big end-to-end model, and you're sort of going to give it these new abilities. It doesn't know how to reason about those abilities, doesn't know how to reason about the failures of those abilities, doesn't know how to detect that there's failures in those abilities. And those are all things that are slightly concerning if you're controlling a robot. All right, I'm done talking. It's these two papers. Tiffany and Jimin are the leads on those. And with that, I thank you.
I think we have time for one or two.
Totally fine. Plus, you should really ask them. I don't know shit. I mean, sorry, this is recorded stuff. Anything. Yeah.
One maybe obvious way to get like that is to basically iterate many parallel iterations and then a top level LM doing the collection. Performance is bad, but why is that not good enough to matter?
No, well, okay. There's at least two questions there. One, I will not claim to know how to get to metacognition, but this is what I was starting to hint at with this sort of changes to your inference algorithm, right? So what we could do is we could start to reason through, be like, how do we operationalize what we believe self-reflection to look like, and then encode that into this, and then we have a whole bunch of different language models that are doing that. I don't think that's necessarily a bad thing. I think that the current trend towards a monolithic model is okay, let's just be spicier and say very silly, right? In the sense that like there's a reason V1 is here, it's different from my auditory cortex, it's different than Wernicke and Broca, right? Like there's regions and there's a reason for that. And so maybe this is exactly the right thing to do. Maybe the idea is to recognize that there's specialization and then there's separate sort of reasoning functionality that should be attached to it. And we're sort of not doing that right now by sort of just hoping we can shove everything through. My only concern, not exactly concern, but I think that is going to be quite a difficult process because it's not the case that we can borrow as cleanly from, for example, the CogSci or psych literature, a sort of procedure for that, right? So metacognition is one of the things that gets sort of characterized, but it's not operationalized. And so what we're sort of advocating here, which might be great, would be an entire research agenda around the operationalization of it. But yeah, I would love to see it. I don't know how to do it.